Welcome. In this video, we are going to review the light field network. So that's a very interesting paper that at the same time allows to reduce the number of function evaluation needed to render like each pixel when evaluating a NeRF model. So that's very interesting. And at the same time, it allows to do reconstruction from S view as one view. So that's a very interesting paper that at the same time makes NeRF faster, but also allow reconstruction from very few views on S view as one view. These are very nice researchers. So let's dive into the papers. They kind of solve two tasks at the same time. We've already covered each of those tasks separately on that channel. So if you did not see those videos, you can have a look at them. So basically, we've seen papers that allow to do like fewer neural network evaluation, such as, for example, AutoInt. But we've also seen papers that allow to do reconstruction from few views, for example, pixel NeRF, GRF. Basically, here what they do, instead of learning the 5D radiance field, well, it still learns it, but instead of having each point, instead of sampling points in the 3D space, and then computing the volumetric integral, they train a neural network that will directly, for a given camera position on view direction, it will directly give the color of the pixel. That seems like interesting. Like naively, that seems fine. But the issue is that it does not ensure 3D consistency. So that's why NeRF is slow, and that's why we are evaluating so many points along the way on solving the volumetric integral. That's to make sure that everything we do is in 3D, and then we are projecting the 3D space into 2D, and making sure that everything is 3D consistent. If we just do that naively, so just train a neural network that will predict for every camera position on view direction the color, we have absolutely no guarantee by architectural design, with no constraints that the output will be consistent, will be 3D consistent. So NeRF by design it's constrained to be 3D consistent, but this approach is not. That's why with the AutoInt paper, we were training the gradient network. By training the gradient network by sampling points in 3D, we were making sure that everything was 3D consistent. So here, to make sure that everything is 3D consistent, again, there is no strict guarantee. So for example, if you show, we are going to discuss about that in a moment, but for example, if you, basically the neural network will learn a prior by pre-training, a bit like pixel NeRF, but in a different way. So if you show it data that it has never seen, or that are too, well, not data that it has never seen, but data that are too different from the one it has seen during training, you have no guarantee that the model will be 3D consistent because there is no hard constraint in the implementation. So basically what they do, they use a hyper network. So basically for each scene, they will encode the scene into latent vector Z. And then they have an hyper network that will predict the weight of the neural network. So yeah, basically that's what hyper network do, but maybe some people are not familiar with hyper network. So basically, the hyper network will predict based on Z the weight of this NeRF neural network. So basically, the hyper network predicts a function as a function of Z, and then the neural network here will predict the color for each view direction. So basically, by pre-training that hyper network on a lot of scenes, then we can show it scenes it has never seen, and it will do it will predict the color of each pixel directly. Now comes the question of how we encode Z. So during training, they said that they could have used other approach, but they decided to do auto decoding. So if you're not familiar with auto decoding, it's like an auto encoder, but basically you have no encoder, you just have the decoder. On the latent, here the decoder is this combination of NeRF and hyper network. But so Z, basically, we assign a Z vector to each scene in the training dataset, and we learn Z with gradient descent. So that makes sense during training. Each Z is learned by gradient descent. But then the question is at inference time, how do we learn Z? And therefore, at inference time, what they do, they fix the parameter of the hypernetwork and they learn Z with gradient descent. On with SU as one image, they can learn Z. So basically Z is learned at the inference time. And once at the inference time, once you've learned Z, it's very fast to predict to make an image, because let's say the image is H, the height is H, the width is W. Then you just need to do H times W function evaluation. While with NeRF you need to do H times W times N, where N is the number of points you sample along each way. So yeah, you are N times faster than NeRF. On here, for example, they give some metrics. Okay, here for example they compare the method. For example, to do inference on a 256 by 256 image, it's taking 2 milliseconds, while pixel NeRF it's taking I think there is a typo here. Pixel NeRF should, I believe, it is taking 3 seconds. So the method is 3 orders of magnitude faster than pixel NeRF. I believe this is not taking into account the fact that they need to learn Z with gradient descent, to learn Z for the scene. But once you have Z that is fixed for your scene, it's very fast to generate new images. Well, you can take off learning Z some amortization. You need to do it only once for a scene, but then you can once you've learned Z, you can generate as many views as you want. On generating each view is taking only 2 milliseconds, but only for a 256 by 256 image. But with NeRF, things are linear, or let's say quadratic. So let's say that you, because you are just thinking about number of pixels, so if 2 times more pixels, you have 2 times more. It's just 2 times. You just need to make twice as many predictions, and it's twice faster, twice slower. Sorry. So let's say that we want to do 512 by 512. It will be 8 milliseconds. That's still very decent in comparison to NeRF or to pixel NeRF. So very interesting paper. We can have a look at some results. Here, for example, you see the input, the prediction. Okay, I believe that's the input, the reconstruction. Oh no, okay. It seems that the views are the same, but there is a bit of rotation. So this is the reconstruction. Here we see more like other like rotations. So yeah, there is much more rotation on those examples. You can see that sometimes the reconstruction is really nice, sometimes a bit more difficult. They also show some comparison to pixel NeRF. Sometimes doing better, sometimes a bit worse. So that's still a paper trained on type problem from I think from 2 years ago. But the idea is very nice. Now could be combined with some other like better architecture, bigger data sets. It could be very interesting for real world applications. So I hope you like this video. I hope it was helpful too. If it was, please leave a thumbs up and subscribe for more videos related to NeRF and to machine learning.